Helium is the second most abundant element in the universe. It constitutes approximately 24% of the mass of all ordinary matter. The sun burns it. Stars are made of it. The cosmos is saturated with it in quantities that make any talk of shortage seem almost absurd. On Earth, it is vanishingly scarce, and we are running out. The apparent contradiction resolves when you understand how helium behaves on a planetary scale. Helium atoms are so small and so light that they cannot be held by Earth's gravity at the upper atmosphere. When helium escapes into the air, whether released from a party balloon, vented from an industrial process, or leaked from any pressurized container, it rises through the atmosphere and leaves the planet permanently. It drifts into space. It is gone at any timescale relevant to human civilization forever. The helium we use on Earth was not captured from the air. It accumulated underground over billions of years, produced by the radioactive decay of uranium and thorium in the Earth's crust. Alpha particles, helium nuclei, emitted during this decay are trapped in the same geological formations that trap natural gas. When we drill for natural gas, we sometimes find helium mixed in, and we can extract it. Once extracted and released, it is not recoverable. There is no process by which humanity can economically recapture atmospheric helium. The geological formations that concentrate it required billions of years to fill. We are depleting them in decades. The medical implications of helium scarcity are the most immediately visible because the connection to ordinary life is direct. Magnetic resonance imaging, MRI, is one of the most powerful diagnostic tools in modern medicine. It allows physicians to image soft tissue in 3 dimensions without ionizing radiation, to detect tumors, visualize brain activity, assess cardiac function, and examine structures that X-rays cannot resolve. It has transformed the diagnosis and treatment of cancer, neurological disorders, cardiovascular disease, and dozens of other conditions. MRI machines operate by generating enormously powerful magnetic fields, typically 1.5 to 3 Tesla, many tens of thousands of times stronger than the Earth's magnetic field. These fields are generated by superconducting electromagnets. Superconductors must operate at temperatures close to absolute zero, roughly minus 269 degrees Celsius. Liquid helium, with a boiling point of minus 269 degrees Celsius, is the only substance practically usable for maintaining superconducting magnets at operating temperature. A single large MRI machine requires approximately 1,500 liters of liquid helium to cool its magnets. When hospitals cannot obtain liquid helium, MRI machines go offline. In the United States alone, there are approximately 13,000 MRI machines in operation. Globally, the number is larger and growing as healthcare systems in developing countries expand their diagnostic capabilities. During helium supply disruptions in recent years, hospitals in multiple countries have reported rationing MRI access, delaying non-emergency scans, and in some cases, shutting down machines temporarily. In regions where supply chains are already fragile, the impact has been more severe. Beyond medicine, helium is irreplaceable in applications spanning the most technologically demanding sectors of the modern economy. In semiconductor manufacturing, helium is used as a cooling medium and as a carrier gas in the deposition processes that build integrated circuits. The manufacturing processes for advanced chips, the kind that power modern smartphones, data centers, and artificial intelligence systems, require helium at specific purity levels that have no economically viable substitute. In space exploration, liquid helium is used to pressurize rocket fuel tanks and purge propellant lines before launch. NASA and commercial launch providers depend on reliable helium supply for every mission. The logistical chain that gets a rocket off the ground includes a helium component that is not optional. In scientific research, helium is essential for any experiment requiring low-temperature environments. Nuclear magnetic resonance spectroscopy, the laboratory technique underlying drug development, chemical analysis, and material science, uses the same superconducting magnet technology as clinical MRI. Particle physics experiments, quantum computing research, and fundamental physics measurements all depend on liquid helium cooling. The Large Hadron Collider at CERN uses approximately 120 metric tons of liquid helium to maintain its superconducting magnets. Quantum computing, widely expected to represent the next paradigm shift in computational power, operates at temperatures even closer to absolute zero than conventional superconducting systems. The most promising quantum computing architectures require cooling to temperatures around 15 millikelvin, a fraction of a degree above absolute zero. This is achievable only through dilution refrigerators that use helium-3, an isotope even rarer than ordinary helium-4, in a system that itself requires liquid helium cooling at higher temperature stages. The technological frontier runs on helium. The geopolitics of helium supply are poorly understood by most people who depend on it, partly because the market has historically been dominated by a single country to a degree that has no parallel in other critical resources. For most of the 20th century, the United States government maintained the Federal Helium Reserve, a massive underground storage facility in the Texas Panhandle, near the city of Amarillo, built during the era when helium was considered a strategic military resource for use in airships. By the late 20th century, the reserve had accumulated a debt from its construction and operation, and Congress passed legislation in 1996 mandating that the reserve be sold off and the debt repaid. The practical effect of this legislation was to flood the helium market with government stockpiles at below-market prices for years, which suppressed the price of helium to the point where private investment in helium exploration and infrastructure was not economically attractive. Low prices discouraged the development of alternative supply. When the government reserve began to deplete, the market found itself with insufficient private infrastructure to replace it. The United States has historically been the world's largest helium producer, but this position has eroded. Qatar, Algeria, Russia, and Australia have become significant producers. Qatar was, until a regional political crisis temporarily disrupted its exports, the second largest producer. The geographic concentration of helium supply, dependent on specific geological formations where natural gas contains significant helium content, means that supply disruptions in any major producing region create immediate global market impacts. The market is also peculiar in that helium is almost always produced as a byproduct of natural gas extraction rather than as a primary target. This means helium production is driven by natural gas economics, not helium economics. When natural gas production slows, helium supply slows with it, regardless of helium demand. The solutions available to address helium scarcity are real, but require investment timescales and policy commitments that have been slow to materialize. Helium recycling is technically feasible and increasingly practiced in research environments. Rather than venting liquid helium as it boils off during use, specialized recovery systems capture the gas, reliquefy it, and return it to the storage vessel. This can dramatically reduce consumption. Some research facilities have reduced their helium use by 70 to 80% through aggressive recycling programs. The barrier is cost. The recovery and reliquefaction equipment is expensive, and the economics only make sense above a threshold of consumption that many smaller facilities don't reach. For MRI machines, specifically, manufacturers are developing systems that require smaller helium charges. Some newer designs use substantially less than the 1,500 liters that older machines require. Completely helium-free MRI technology, using alternative cooling approaches, is in development, though it has not yet reached commercial deployment at clinical scale. New helium discoveries are being made. Tanzania has large identified helium reserves in geological formations associated with the East African Rift, a discovery announced in 2016 that represented the first major new helium find in decades. Development of these reserves is ongoing but requires significant infrastructure investment. The fundamental constraint remains: we are extracting a non-renewable resource whose replenishment operates on geological timescales. Even with recycling, efficiency gains, and new discoveries, the long-term trajectory of helium availability is one of increasing scarcity and increasing cost. The technologies and medical procedures that depend on it will need either to adapt or to pay progressively more for access to a resource that cannot be made. There is something clarifying about the helium crisis in the context of thinking about resources and civilization. We are accustomed, in discussions of resource scarcity, to thinking about energy, oil, natural gas, coal, or about bulk commodities like water and sand. These are resources whose scarcity we understand intuitively because we use them in quantities we can visualize. Helium does not fit this mental model. The quantities used are invisible. The connections to medical care, to computing, to scientific progress are not obvious. The depletion happens in industrial facilities, not in landscapes we can observe. But the consequences of getting it wrong are concrete and immediate. Hospitals that cannot run MRI machines. Research programs that cannot maintain superconducting experiments. Manufacturing lines that cannot produce advanced chips. A quantum computing future that cannot arrive because the cooling infrastructure doesn't exist. We are releasing into the atmosphere, permanently and irrecoverably, one of the rarest and most useful substances on Earth. We are doing it because balloons are fun and because we haven't been asked to pay the full cost. At some point, the bill arrives regardless.